All right. Well, congratulations if you've made it this far. Um, we're diving deep into quantum mechanics here, guys. And I know there's a lot of new concepts, and you just got to hang with me. This is all going to tie together and get us back to the periodic table and things that we know and love. All right. But one more thing that we have to go over. It's another one of these crazy principles, these crazy truths that we know in the universe is called the Heisenberg Uncertainty principle. And this basically tells you that you can never know something exactly. All right. And specifically, okay, look at this equation saying change in x. Okay, so this is change in position. Let's say you're trying to measure a particle and you want to know where that particle is. That particle could be at different locations each time you measure it. Okay, so the difference in where that particle is in its position, in its x position, times m times v, mass times velocity, that's the change of its momentum, will always be greater than or equal to Planck's constant divided by 4 pi. Now, where does this 4 pi comes from? Don't worry about it. You know, I couldn't tell you without consulting some pretty in-depth quantum mechanics physics books, and I don't know that off the top of my head, okay? But basically it's telling you, you can never know exactly where something is or exactly its momentum, which is its mass and its velocity. So its mass, velocity, and position, you can never know 100% precisely, okay? Now, h is Planck's constant, right? We know that that's a very, very small number, okay? It's a very, very small number. And so day-to-day life for us walking around, we're not randomly, moving through walls invisibly, okay? We're not teleporting from place to place because h is very small. We're not jumping our x position around. But when you start zooming into the atomic level, right, now h becomes significant, and that's where this Heisenberg uncertainty principle starts getting relevant. So you can see, buy tickets here for a lecture on Heisenberg uncertainty principle. I can tell you the time or place, but not both, right? So if you know the position very accurately, then you won't be able to know the momentum as much, right? Because this delta value of the momentum will have to go up if this went down, right? It has to be greater than this value, or vice versa. So if you know the momentum very precisely, you won't be able to know the position very precisely. So that's what this first bullet point says. You cannot know both the position and the momentum with great precision of a particle at a given time. But you still can know roughly where it is, and pretty darn good, right? H is pretty small. So we know the region inside the atom where the electron. We're talking about electrons now. Electrons are really small, so this is why this is important, because then H becomes noticeable. So we can do some probability, basically. And we can figure out where most of the time an electron is. So that's what we do in our quantum mechanical models of atoms, okay? And so this is why the Bohr model is totally wrong, because the Bohr model had those fixed orbits. It's not like that. There's some uncertainty intrinsically to the system that you can never get around no matter what type of equipment you use. It's humanly, physically impossible by the laws of quantum mechanics. Unless quantum theory ends up being wrong, right? It's an approximation. That's the best we know. So electrons don't move in predictable patterns. Instead of using orbits, right, which is a predictable pattern, we know exactly where the stars are going to be. We know exactly where the planets are going to be, right? Those are moving in orbits. We're going to use a different term called orbitals. And this is going to be basically an orbit, sort of, but with probability, okay? So it's regions of 90% probability. And so this is going to be a probability map, okay? And so it might look like something like this graphically. We're like, hey, we know electrons most of the time are in the center here, so we'll give it a darker color. But they could be also on the edge, so we give it a lighter color. But most of the time they're not going to be way out here, so we're not coloring anything out there. So Schrödinger figured out the equations to figure out how all these probabilities of where the electrons are, how they interact with one another. And he comes up with this gnarly equation, okay? And it looks simple at first. It's, okay, H times psi, this is a Greek letter. Psi stands for wave function, that's a function, equals energy times psi. That looks pretty simple, but then if you know what H is, it's called a Hamiltonian, and E is, you get this nasty thing, okay? This is H bar, which is actually, has H in it, squared, and then there's a second derivative here with respect to position and time, and this is only the one-dimensional Schrödinger equation. We have to actually have X, Y, and Z in here, so this is already approximation. There's an imaginary number in here. Okay, this is gnarly math, gnarly physics here, and we don't need to know this, okay? I'm just trying to give you an appreciation for what this is. Out of all this garbage, okay, it's not garbage, it's beautiful math, okay? But out of all this beautiful math that to us looks like garbage, you get psi, which is a wave function. And that tells you in three-dimensional space where an electron probably is with some probability. That can give you a shape of orbitals, okay? And that's really what you want. Yeah, H is Hamiltonian, it's crazy math stuff. We don't have to really worry about it. Luckily, Schrödinger did this all for us, and we're just looking at pictures now, okay? And so psi will tell us, it turns out psi squared, okay? Psi squared tells us a probability distribution of where an electron is. And from that, we can get shapes. So one of the shapes of where electrons can be looks kind of like a sphere. It basically is a sphere. And you can go on this website and play with some of these orbital pictures if you want. But basically what I want you to know and take home from this video is quantum mechanics is crazy. We don't know where an electron is ever with 100% certainty because of the Heisenberg Uncertainty principle. But we can still get useful information from the Schrödinger equation, which basically tells us pictures in three-dimensional space of where electrons are. Those are called orbitals, not orbits. It's not like a solar system. We're going to be talking about orbitals in the next video.